Hello, everybody.
Evening, Professor.
How's it?
Welcome to your last day of concrete.
Isn't this the beginning of concrete?
The beginning. Sure. Welcome to your last free day of concrete. Next time will be the final, and then you can start your career in concrete design. So waiting for a few more people to join in here.
Are you watching the Lakers tonight?
Basketball's on? I thought they canceled basketball.
Yeah, it's back. This is the first game, I think. So it's Lakers versus Clippers.
Oh, no kidding. How are they doing that? Is it a empty auditorium? Is it, the Staples Center, but empty?
No, it's funny. They moved the entire league over to Florida. They call it a Disney bubble because no one is allowed to go in or out, and all the players and staff are staying in hotels in Disneyland. And they're going to play all the games in a gymnasium that Disney has.
You're serious?
Yeah.
I'll be darned.
The National Women's Soccer League, the NWSL, just did the same thing. They finished a month-long tournament in Utah.
Huh.
And they had like over 2,000 COVID tests, all negative. They finished the whole tournament. It was a really big success.
Wow. So, but you guys are saying not just the players and the support, but the actual fans got tested before they could watch the games?
There's no fans.
Oh, okay.
It's like families, like immediate family members, I believe.
Okay, so they're playing these games, and then I guess they're televising them for all of us, but nobody can actually watch them if they're not like part of it.
Right.
Okay. I'll have to ask my son about that. He took the last week with all his buddies and did like a trip to Grand Canyon, and then Moab, and then Zion, and so he'll be back tomorrow. He's the sports fan of the family, and I'll have to talk to him about that. And as you can gather, I'm the nerd of the family because, I like concrete. Okay, I guess we have who we're going to have tonight. My plan for tonight was we're going to finish up what we had started on retaining walls and then just open it up for as long as you guys want for any questions that you may have. And that is about it. Before we start the end, the last of the last lecture, do I have any questions about homework or what we talked about last time or anything? Any questions at all?
Hey, Professor, I had a question on homework 8.
Mm-hmm.
When I was finding my RN, I ended up getting something that was smaller than the values in the table to find my my row for the So I was wondering if that is like a red flag, like that I did something wrong, or do I just go with the row minimum for temp and shrinkage, or?
Okay, no, thank you. Thank you for asking that question. No, it is not. It is not a flag that you did something wrong. Remember that for footings, unlike beams, footings are usually sized in their thickness for shear. Beams are usually sized in their depth for flexural resistance or deflection or cracking. And then we just design around that for shear, usually. But footings are the opposite. So the footing, if you did it correctly, you basically sized it to handle the shear without any shear ties. So the consequence of that is you have a footing that is pretty thick, and it's a lot thicker than it needs to be for the bending moment. So it's fairly common in footings to have the flexural demand be significantly less than the minimum required uh, minimum rows, basically the minimum area of steel for flexure. And like we discussed in the lecture, some engineers will use the minimum steel required for flexure as the minimum, but the code actually says that you can go down to shrinkage and temperature steel as your minimum, which is what I'm teaching. So I'm teaching your minimum is shrinkage and temperature steel, but it's fairly common in footings, again, because they were sized in their thickness for shear, it's fairly common in footings that the flexural demand will be less than the temperature and shrinkage demand. So no, you didn't do anything wrong at all. You just need to recognize that, okay, which one of these two, the flexure or the temperature and shrinkage, which one of them demands more steel, and make sure you meet that.
Okay. So would that like result in a higher price for the footing if you use uh, temp and shrinkage steel because it's like
Yes,
deeper?
yes, but it's not a higher price than what somebody who knows how to do footings ought to expect.
Mm.
If you're a contractor or a builder, whatever, and it's your job to build footings, then you're used to a minimum amount of steel. You know that you haven't built any footings that are going to have less than 0.0018 times the gross area in steel. So you're used to that. And so what that means is contractors who build footings, if it's 2 feet deep, you're used to number 6s at 10 or number 8s at 12, whatever it ends up being, that's kind of what you're used to. If the footings are 4 feet deep, which they are sometimes, then you're used to a good amount of steel in there, number 10s at 12 or something like that. And so if the drawings called for 4 feet deep footings with number 5s at 18, something's wrong. And a good contractor would clearly is like, oh, whoa, that ain't right. And they would recognize it right off the bat.
All right. Thank you.
Okay, hopefully that made sense. And I've designed some footings, by the way, that they're spread footings, but they go under shear walls. So when you have a footing under a shear wall and the shear wall is being rocked by an earthquake, it pushes down really hard on one end and it's actually lifting or pulling up on the other end. It's trying to roll the wall over. And that puts a huge amount of shear into concrete footings. So I have designed footings that are 4 and 5 feet thick under good sized shear walls. Do I have any other questions before we get started for tonight?
Yeah, I was working on a project for another class,
Uh-huh.
and I was designing a footing for a post for a deck, and it was really small. It ended up being like an 18 by 18 by 8.5 footing. And then I was
Okay.
wondering if at that point, like I couldn't find anything on ACI, like if a provision like minimum or like size of a footing where you don't need steel. And I'm wondering if you could point me to somewhere where it says it.
Okay. All right. Um, yeah, I can. I am not aware of anywhere in the code that says that a footing has to be a minimum thickness. That's kind of an interesting question. There may be something in there. I'm not aware of that. So I think you can make footings pretty darn thin and small, uh, because at what point does a footing, a slab on grade could be 4, 5, 6 inches thick, put a post on it and now it's a footing instead of a slab on grade. Even sidewalks are like 3 inches or 2.5 inches thick. So I don't think the code really has a minimum, but in terms of the steel, that one I can help you with, I think. in ACI 318.14, there is a chapter. It's been carried over from years and years and years. And I am looking for it. Okay, so they moved it to chapter 14. There's a chapter called Plain Concrete. And it's not very long because usually people don't do it. But if you wanted to design a footing that had no steel in it, no shear steel, no flexural steel, no temperature and shrinkage steel, I mean, no steel, other than just burying a CMU block in the ground and putting a 4x4 on it, other than doing that, I think you need to look at chapter 14 for plain concrete.
Okay. Yeah, it's I checked the shear demand and the capacity, and I think the capacity ended up being like 7,000 something, and the demand was only like around 100 something. It was much, much, much greater. So that's why I was wondering if it's unnecessary to do all that calculation.
Your load is 100 pounds.
Yeah, I believe it was like 100. No, sorry. Actually, yeah, it was something like around 180, I think, and then the capacity was like 7,000 something. Yeah, extremely over designed, right?
Yeah, that may be, I don't know. That's a funny one. If you had to actually put it on a structural drawing, then you would have to have some calc for it. But I mean, the load that you're talking about is almost in the realm of get like a 5-gallon bucket from Home Depot, fill it up with wet concrete, and just shove the post in there and bury it. It is
Yeah, I'll be sure
very,
to include that in my report.
yeah, it's very non-technical. But if you actually had to show it on a drawing, then it has to conform. If it's part of a building, and even if it's just like you have a porch and you have an overhang and this thing's supporting like 10 feet of light wood roof over a porch, yeah, you still have to conform to it. It's an interesting question, though. I'm just kind of looking through real quick what is on chapter 14 for plain concrete. Let's see. Members and building structures, building and non-building structures. This chapter shall not govern the design of cast-in-place concrete piles or piers embedded in the ground. So don't call it a pier. Plain concrete shall be permitted only in cases members are continuously supported by soil or supported by other structural blah, 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 which, oh, yeah, you could do it. Yeah, okay. So take a look at chapter 14. And basically all it is, it just takes all your phi factors, your 0.9 and your 0.75, and it knocks them way down. But if you have a capacity of 7,000 and you're looking for 100 or 200 pounds, you could have a phi of 10%, it would still work.
Yeah, definitely. Okay, thank you.
You're welcome. Any other questions?
Professor, I just had a quick question on
Sure.
the footing. So whenever we have pretty much when I was looking through your examples, it was example 4 and 5 that we designed. And in example 4, I mean, it was just like a wall and with like a footing, like a continuous footing. We didn't, we only calculated for the shear once. We didn't calculate for the punching shear. Why didn't we calculate for the punching shear of the continuous wall? Can't the wall go through the slab?
Good question. Good question. Yes, the wall could go through the slab, but in a way that is pretty much what we're already checking with one-way shear. Let me draw an illustration. Okay, so a continuous footing looks like this. And the loading comes from a wall that looks like this. Okay, so I'm looking straight down on a wall and a footing, like in plan view. And if this thing is going to fail at all in shear, then the way that it's going to fail is it's going to have to shear through here, just like that, right? So if it fails in shear, it can't just fail in one little area. It's got to fail all the way along this whole line right here in order to fail in shear. If it was going to fail in shear in the other direction, which we didn't really talk about a whole lot, but if it was going to fail in shear this way, it would have to shear all the way up and through the wall. So that's why we don't even check this direction, because it would have to take the whole wall out with it. And that's not a likely failure mode. And I just took out my whole footing. So let me put my footing back. Okay, so there's my whole footing. Now, if I was going to check this in two-way or punching shear, then if you think about how is it actually going to fail, well, it's going to punch through the whole slab just like that. So now your failure mode is on both sides. Well, if you check one-way shear on the one side and you check the punching shear going along this whole perimeter here, because it's not going to fail anywhere in between because it's got to go through the wall. So the only place it would fail is out here where you actually don't even have any concrete. So this is what I'm trying to say. This failure mode and one-way shear are really kind of the same thing at this point.
Okay, it makes sense. It really does make sense from this point of view.
As opposed to a spread footing with a column on it that's trying to punch through it. And with a spread footing, the one-way shear is going to shear the whole footing through this way. And the punching shear is going to try to punch a hole right through the center. And so now you can see that this perimeter of failure surface is completely different than this line of failure surface. Some cases this might control, other cases this might control. So you have to check both. But clearly from the illustration, you can see that they're completely different. So this is one mode, this is a totally different mode. In the strip footing, they're kind of the same. So we don't check punching shear on a strip footing, we just check the one-way shear.
Makes sense. Makes sense. Thank you.
Okay.
And do we have time for one more question? It's just literally about these.
Yeah.
Yeah. Okay. Whenever we are finding the LD, we use the one that just goes for the rebar for both of these cases. We don't look at the hooks or anything. Is there a reason for that? Is there a reason that we only look at, the rebar not failing in the footing? Then how does it connect with the column / the wall?
Okay. Good question. Let me draw a different diagram. Okay, so now what I'm looking at is a side view of the footing. And there's a column. So this is a spread footing. This is a column pushing straight down on it. What we've been talking about so far is really the shear and flexural capacity of the footing itself. So these rebars are down in here. And the LD that you're talking about means that I need to be sure that from the critical face of the column to the end of the rebar, I have enough development length here to develop this bar so that at the point where you need it the most, you have the full yield capability of that bar. If I had some kind of a situation where I don't have that and I can't get that, In other words, I can't make the bars smaller, or I can't make the footing bigger, whatever the issue may be, it most certainly can happen where I don't have the capability of doing that. Then I would put hooks on it, like so, that would develop this rebar much, much quicker than if it was just a straight rebar, like we talked about in that lecture. Okay, but now what you're talking about, well, we didn't really talk about this a whole lot, but what you're talking about is the rebar in the column is coming down into this footing, like so. And it's really kind of the same deal where you have to check this. So from the critical faces here, so from here to the bottom of these bars here, do I have enough room right there to develop the bars coming out of the column? And usually the answer is no, usually. So the usual situation then is that we put hooks on these bars to help them develop in a much shallower system depth here. If it's a very deep footing, or even like a pile cap, then you very well may have enough room here to develop those bars for the capacity of the column. But in normal situations, if this is like in the 2-foot range, then if these are number, I don't know, 8s, 9s, or 10s, then 20 inches or so is not going to be enough. And so we put hooks on them. And so what happens is in the real world, they dig the footing out. I kind of messed that up. All right. Well, anyway, they dig the footing out. They put the rebar in the bottom in 2 layers and chair it up on adobes off of the ground. And then they put in L bars in here and they tie them to this mat down here so they kind of stay in place. And these L bars will stick up into the column by 6 or 8 feet or whatever. And then they pour the footing. And they pour the footing right up to the top of the footing. That's your top of concrete. And these bars will be sticking out. And then another crew comes in and starts splicing these rebars with a column cage that gets dropped on top of it. They tie it all up together. And then in a separate operation, they start pouring in all the columns. And they just keep going up from there. Did that help? Did that hit the question?
Yes, yes. I was just trying to see if you asked that on like a final, how we can check it. No, I kind of got it.
Okay.
Okay, thank you.
Okay. And I won't. I'm not going to, because we didn't really talk about this a whole lot. So I'm not trying to like really confuse everybody. This was in those details that you just really don't have enough time to hit in your undergrad for concrete design. But I'm more than happy to walk you through it so you can kind of picture how it goes, but I'm not expecting this sort of detail to be checked on the final.
Okay, makes sense. Thank you.
Okay. Anybody else? Any other questions? All right, then let's see how far we get on this. Where we started last time was the design of a retaining wall, a concrete retaining wall built integrally with a concrete footing. And then what we did last time is we calculated what the loads were at a service level so that we could do our 3 service level checks. The 3 service level checks were that the bearing stress in the soil is not greater than the allowable, and that the tendency for the whole assembly to slide has a 1.5, 1.5 factor of safety, and the whole assembly tending to rotate about the toe has a 1.5 factor of safety. So that's what we talked about last lecture. And that's where we left off, if I remember right. So where we're going to start now is start talking about the concrete portion, the actual design of the concrete. So the first half of the example was dealing with soil allowables and parameters. and the second half is dealing with the actual concrete design. So for the concrete design, we're going to start with the concrete wall. And I don't have an illustration because I kind of broke it up. But remember, the concrete wall was shaped like kind of like that. That was the shape of the concrete wall. So it's 18 inches thick at the bottom, and it's only 12 inches thick at the top. And we have rebar on the back face, like so, because the tendency is for the wall to get pushed to the left. So that puts the right-hand side in tension and the left-hand side in compression. So this is what we're dealing with. The thickness of the wall at the base is 18. We have 3-inch cover to our steel because we're right up against dirt. And so I assume then that D is 18 minus 3.5. So from the edge to the steel, that's my D of 18 minus 3.5. So D is assumed to be 14.5 inches. My linear load is the gamma EF, is the equivalent fluid pressure, times H is the height of the wall times the load factor. Load factor for active soil pressure is taken to be 1.6. And now I have an illustration, so I can dispense with this one. Okay, so now we're just looking at the concrete wall portion. So I don't need the bearing or the lateral stress over here just yet. I'm just looking at what's being applied to the wall. And this pressure is tending to push the wall to the left. So it would fail in moment right at the base here. And shear demand is D up from the base, just like we did with concrete beams. So for flexure, I take my equivalent fluid load, 40 pounds per cubic foot, times the height of the wall is 17.5 feet. The width is a 1-foot strip for design, and my load factor is 1.6. So I get 1.120 kips per lineal foot. That's a uniform, or sorry, that's not a uniform, that's a triangular load that maximizes at the bottom and is 0 at the top. So for shear, then I'm going to calculate what my WU is at this point, and that is 1.043 kips per lineal foot. So again, this is a triangular linear load. The load is 0 at the top, and it maximizes at the bottom at 1,120 pounds a lineal foot. It's a little bit less D up from the bottom at 1,043 pounds per lineal foot. Is that clear for everybody, or do I need to elaborate?
It's all right.
Okay. Well, if anybody feels differently, please let me know. So we can calculate the flexural moment at the base here. The moment is the linear load at the base times 17.5 is the wall height over 2 because it's a triangle times a moment arm of 17.5 feet over 3 because the center of gravity of a triangle is 1/3 up from the base. So this is the load times the height times the moment arm. And that gives me 57.2 kip feet of moment. And now this becomes a singly reinforced rectangular beam problem. In fact, I can kind of elaborate it on this a little bit. If I take this and I look at a section, then that section is going to look like this. And on the back side, I have my rebar. okay? And this is 12 inches wide because we're always designing for a 12-inch strip. And from here to here is my D equal to 14.5 inches. So as you can see, it looks a lot more complicated in the side view, but from a top-down section view, it's just a singly reinforced rectangular beam. So being a singly reinforced rectangular beam, now we can use our well-known methods for sizing the steel, where I can find my R sub n index, mu over phi bd squared, where I take my mu times 12 over phi bd squared, and I get 304 psi. From my tables, I get a rho required of 0.0054. So my area steel is 0.0054 times D times B is 0.094 inches squared per foot. So with number 7 bars, my area steel per bar is 0.6 inches squared. So my required spacing is my area steel per bar over my required area steel times 12, 0.6 over 0.94 times 12, 7.66 inches. So I'm going to use number 7s at 7 inches on center. That's my design. Now, so what is my actual provided steel? And I see this getting confused a lot between required steel and provided steel. So remember that the 0.94 here is what's required from your RN index, but that's not what you're providing. What you're providing is number 7s at 7. So we need to calculate the area steel that we're actually providing. 0.6 times 12 over 7 gives me 1.03 inches squared per foot. And I've probably said this, how many lectures do we have? 18, so probably about 1,800 times now. Do not stop here. Just because 1.03 is more than 0.94 does not mean anything to me. This is just an intermediate step, but this is how much steel per foot that you're providing in this wall. Rho is 1.03 over 12 times BD, 0.0059. So we're doing our check here using the tables. 0.0059 is greater than 0.0033, the minimum for flexure, and less than 0.181, the maximum steel to keep epsilon sub t at 0.005. So I did a shortcut here. I just went straight to the tables and looked between the maximums. So we must always, always, always check that phi mn is greater than mu. For a singly reinforced rectangular beam, I can use my familiar equation and I plug in my values with my provided steel. D is assumed, my provided steel, 12-inch width. This gives me 764.4 kip inch or 63.7 kip feet. 63.7 is greater than 57.2. Therefore, my design is acceptable with my number 7s at 7 inches on center. Any questions about that portion? Okay. To check development into the footing. Edgemon, I think this is pretty close to the question you just asked.
Yep. I
Okay,
just saw
good.
it.
Awesome, and I totally forgot I put this in here, so here we go. All right, we're gonna check our development into the footing. LDH is the greatest of the following. Fy psi e psi c psi r over 50 lambda square root f prime c dB, or 8 dB, or 6 inches. Now, an assumption that we're making, I forgot what the thickness of the footing was, but we had that in the original problem statement. But the assumption that you can see kind of built into this is that number 7 bars will not develop in the space that we have if we do not hook them. That's kind of just inherently assumed here. And I think you could pretty quickly determine that that is correct. Again, I don't remember how thick the footing was. It was 20 inches or 24 inches, somewhere in that ballpark. And so 20-inch development without a hook for number 7 just isn't going to make it. So we know we have to hook them. We're just going to double check that even with the hook that I have enough development length here. So LDH is FY. I guess I didn't do each one of these individually. Darn, I should have. I don't remember what that 0.7 was. Psi sub C. Okay, hold on a second. I got to know why that's 0.7.
Professor, that's 0.7 because it says number 11 bar or smaller hooks with side cover, not extending 2.5. That's from your notes.
I think you are right on the money. But it doesn't mean I shouldn't have put it in this. But I think you're absolutely right. Here we are. Okay, modified for deformed bars in tension, for hooked bars in tension, size of C, number 11 bar and smaller with side cover and back cover 0.7. Yep, that's exactly right. Okay, sorry I didn't put it in here, but yeah, that is from the previous lecture. So in a footing, I've got tons of side cover, I got tons of back cover, so there's no issue with cover. And number 7s are smaller than number 11s. So we're taking that 0.7 factor. Normal weight concrete, 4,000 PSI. Number 7 is 0.875 inches in diameter. So I need 11.6 inches minimum for that hook. Or I need 8 times 0.875 is 7 inches or 6 inches. So of course, it is the greatest of these three, 11.6. 11.6 controls, but is much less than 27 inches, so we're okay. I guess we put a 30-inch footing on this one. Okay, shear design. Now we're back to the wall, the shear design of the wall. So the linear load at D up from the bottom or top of the footing, D up is 1,043 pounds per lineal foot. So shear is 1.043 times 16.29 feet over 2. It is over 2 because remember the loading is a triangle. So my shear demand is 8.5 kips. My shear capacity of the concrete, 2 lambda square root F prime C BWD. So normal weight concrete, 4,000 PSI, B is 12, D is 14.5 assumed. I have a capacity of 22. My phi VC is 0.75 times 22 is 16.5 kips, greater than 8.5 kips, so we are okay. It would be very unusual and probably very expensive to try to use shear ties in a wall like this. So you really want to proportion this like a footing so that phi VC alone is greater than VU without the use of steel. Okay, horizontal steel. This is something we haven't really touched on, but for a concrete wall, you do have a minimum amount of horizontal steel that is required, and as controlled by ACI 318 section 1161 and table 1161. For bars greater than number 5s, the minimum row is 0.0025. So if I take a 0.0025 times 12 inches wide times 14.5 D, I get 0.435 inches squared. With number 6 bars, area of 1 bar is 0.44. So I go with my AS per bar over AS required times 12, gives me just over 12 inches. So I'm going to use number 6s at 12 inches on center. And that's not really too clear. Let me sketch that real quick, just a little bit bigger scale. Okay, so what I'm saying is the main flexural reinforcement here is your number 7s at 7, which is what we designed. But then you also have to provide a minimum amount of horizontal steel, which is here, like this. Now, in a non-seismic wall, this isn't really doing a whole lot. In a seismic wall, this is your shear reinforcement. But in a non-seismic wall, like a retaining wall, what this steel is really there to do is to control cracking. You pour this wall, and the concrete is going to shrink. And as it tends to shrink, it tends to crack up the face of the wall. So you need some kind of a crack control, kind of like temperature and shrinkage, but for walls. So this steel is going in and out of the page, obviously, and it's there to control cracks from the wall shrinking in the longitudinal direction. This steel does not provide any shear capability. Okay, I want to be clear about that because I said in a minute ago you don't usually see shear steel. If this wall were to fail in shear, then the shear failures would look like that. And so the only kind of steel that would help that is if you had steel going through the thickness of the wall this way. And that's what I'm saying. You don't see that in walls. That would be prohibitively expensive. That would actually be like shear ties going this way. And that's not something we do, okay? So if you're having a shear problem, you just make the wall thicker until you don't have a shear problem. Does that make sense to everybody?
Yes.
Okay. Everybody clear? I mean, this is an overall kind of the design sketch of the design of the wall portion. Does this make sense? Does my little blow up of what this is, does that make sense? Or do I have any questions on this?
I'm good.
Okay. All right, now what we're going to do is look at the design of the footing, this portion of the concrete down here. At the toe as well as the heel follows the design process for footings as described in lecture 15. So actually I don't. Let me go back there a minute. Let me talk about this a little bit more. From the current slide, there we are. Okay, so I was really struggling with this, whether or not to go into the actual design of this footing by itself. And I started building into it. It just got massively complicated, like really quick. So it would have easily doubled the length of this presentation. And so I had to make a decision at some point. It's the classic decision that I struggle with. Is what I'm presenting going to help you guys understand this, or is it going to make it more confusing? And ultimately, I dumped it because it was getting really confusing. But let me slow down for just a moment and explain why it was getting confusing. So at least you have a grasp of the concept. When you have a footing and you have a retaining wall, then the load from the soil is trying to turn the wall over, which is trying to shove the toe into the ground and is trying to lift the heel off of the ground. So you have a bearing stress on the soil when you factor it, especially when you factor it, you'll get a bearing stress that may look like this. You don't even have bearing stress over here. dirt cannot hold concrete down, so you don't have any negative stress over here. What you have is just a chunk of soil under a lot of compression, and then kind of the backside of the footing has no load on it at all. But at the same time that you have the soil producing this kind of stress, which is pushing up on the footing, at the same time, you have that giant wedge of dirt back here that is pushing down on the backside of the footing. So draw some little arrows on here. Okay, so is this reading? Are you guys seeing this?
Yes, we are.
Yeah.
Okay, so this is why it got pretty complicated pretty quickly. And I basically decided that going through this whole example, you can't just go halfway. You're committed. If you're going to do it, you got to do it. And I got about halfway through it, and I said, they're going to try to shoot me. This is just so complicated. But I'm just trying to explain why it got so complicated. So this soil pressure pushing up on the footing is trying to fail the footing right there. So you have to design your steel at the bottom of your footing to resist that moment. Okay, so you take the portion of the soil loading, which is not linear or it's not uniform. It is linear, but it's not uniform. So you have to calculate what the pressure is here, what the pressure is here, find the average times the moment arm, find the moment at this face, and then design this flexural steel to resist that moment. But at the same time, you have the soil on the backspan pushing down on this thing. This whole thing's trying to lift up, and all this soil up here is pushing down. So it's trying to fail the footing there. And you have very little of the actual bearing soil pressure pushing, kind of equalizing it. You have very little of this to balance this. So it's mostly just this trying to break off the backspan of the footing. So it wants to crack here. And what you got to do is come up with another steel layer up here designed to resist the negative moment, if you will, at this point. So you can see why I just left it as it is. Any questions? Wow, did I put everybody to sleep? What happened?
Trying to absorb it.
Yep.
It's not that easy.
Yeah, we're still taking it in.
Yeah.
I'm still taking footings in, so.
Okay. All righty. Well, like I said, I made a conscious decision that working through the example of what I drew right here would easily double the slide count of this presentation. So it would have been a whole nother hour and a half easy just going through this. And I'm pretty sure I would have left half of you going, huh? What? Anyway, I made a conscious decision that this would not help. It would just make it more confusing. So I just wanted to kind of outline for you why it would have been so confusing. And this is what you would have to face in the real world if you're designing these. But this takes a bit more experience and just experience and practice working with reinforced concrete. So here we go. It all goes bye-bye. And that really is the end of my presentations. So what I can do, we still have over an hour that I have allocated to just, I'll be here for as long as you want to talk about whatever you want from the beginning. Okay, so I got just white paper here. Okay, so first of all, do you guys have enough questions, you think, that we should take a break? Or, and I'm totally cool either way, but do you think you have enough questions that you want to ask? And I know it's kind of hard because nobody's talking to each other, but should we take a break or should we just power through?
Professor, to be
Let's
honest,
power through.
I have like 4 or 5 questions. So that's just me. So I'm just being honest.
Okay. Well, for everybody else, you guys want to take a break or do we want to power through the questions?
Yeah, break is fine.
Okay. All right. I'm cool with that too. So let's take a break. It's 5:51, 5:50. Let's come back at 6 o'clock and we'll wrap it up. So reconvene at 6 p.m.
Perfect.
Hello.
Hi, Professor.
All right. I think everybody's on here. So let's open it up for questions.
Professor, may I ask mine?
Mhm.
For the LD, the development length, there's 4 of them. And like, what I had the problem with is whenever we're trying to write the size in our cheat sheet, just writing those 4 literally takes the whole cheat sheet to like memorize. So I was wondering if you want us to, I don't know, print the notes, print the portions of the size that we're gonna use, or is there like a specific one that we have to, target for the final?
Well, you can have your textbook for the final. I assume that you're going to have your textbook. So if it was me, I wouldn't write out any of them onto the sheets. Basically, what I would do is just have a little section on there that says for bar development. And then, as you said, there's 4 that we basically talked about. There's straight bar, there's hooked bars, there's headed bars, and then there's compression. And I would just write those 4 words, straight, headed, hooked, compression, and then put the page number of the textbook where you would go to find that information if you need it.
Okay. Okay, that actually makes sense. And then for the same topic, it's I was reading somewhere that it says the KTR may be taken as 0 for simplicity. Is that true for, all the time? We can take the KTR as 0?
Yes, unless I would specify not to. If you take KTR to be 0, you're being conservative and you'll get a longer development length. So there's all kinds of instances in ACI code. It's all over the whole from front to back, where if you want the simplest but conservative, do this. If you want to be more refined, do this. And then you can do the most complicated version and do this, but you get the best answer. That happens throughout the entire book. It's kind of one of their ways of doing things. We talked about that in shear design. This is the simplest way to do it, but this is a more refined way to do it. We talked about that in slender columns for the effective moment of inertia, and so on and so on. So if the problem stated determine KTR, then you have to determine KTR. But if the problem statement was just, what's the minimum development length, yeah, you could do that.
Okay, makes sense. It makes a lot of sense. Thank you. I'll let other people talk.
Professor, can you extend on that slender column?
On
I'm
the
not,
slender column, I'm
yeah,
sorry.
I'm not quite well with the slender column concepts. Like what's more important about the concept of slender column?
Same with me.
Well, okay. So columns are in the scope of the test. And we had short columns with concentric axial load only. We had short columns with axial load and moment, which required building an interaction diagram. And then we had slender columns, which have axial load and bending as well, but they also have P delta effects. They have secondary effects because the column will deform and it adds to the original moment. So those are like the 3 broad categories, and we had like a lecture on each. Short columns with concentric axial load, short columns with moment and axial load, and slender columns. So that's the broad category. Now, all 3 broad categories are within the scope of the test, but again, I have to be cognizant that one slender column problem, if I was to ask you from, design this thing from beginning to end, it could be a 4 or 5 hour problem on a 2-hour test. So I'm limited in what I can ask you, but any of the concepts are fair game for all those categories. Does that help? And maybe refine your question.
So for the slender column, are we supposed to grasp the whole concept of like slenderness ratio, effective EI, the radius, the IG over AG? Are we supposed to, and also the delta?
Yes, you are supposed to grasp the concept. And the concept is that with a slender column, the moments cause the column to deflect. And that deflection causes an eccentricity on the axial load, which axial load times eccentricity causes more moment. So the basic concept is the loading causes the column to deflect, and then the axial load causes it to deflect more, and the more it deflects, the more moment it gains. And it's a buckling effect. And it will either catch itself or it won't catch itself. It'll either converge or it won't converge. And what the code does is has us do a procedure to check whether or not we think it's going to catch itself and whether or not it has enough strength to catch itself. That procedure for slender columns is the moment magnification procedure. And the moment magnification procedure, you have to calculate the critical buckling load. And then with the critical buckling load and the CM factor, you calculate delta. And delta is a magnification of the original moment. So I'm just getting very broad terms. I'm not getting into the weeds here. We did it in the lecture, but just in very broad terms, the whole procedure is that you calculate a delta to magnify the original moments to account for the secondary effects. In the calculation of delta, you have to calculate the Euler's buckling load and the CM factor. Euler's buckling load has the stiffness built right into it. In fact, the stiffness is the most critical part of the buckling load. And in that stiffness, you have to calculate an effective stiffness, which is stiffness is just moment of inertia times modulus elasticity. The modulus doesn't get changed, but the moment of inertia, you can't just use the gross moment of inertia, you have to use an effective moment of inertia. And that is where we talked about those three different ways of doing it of varying detail.
Okay, thank you.
So yeah, there was a lot there. There was a lot there. We had some tests to see, is the column braced or not braced? Is the column slender or not slender? And our test for slenderness involved a KL over R check. And so you calculated KL over R, and then you checked it against these criteria. And if it was less than, it's not slender, don't worry about it, just design it as a short column. If it is greater than these criteria, you have yourself a slender column now, and you have to go through the whole procedure to calculate delta. So again, upfront and honest, I am not going to give you a question that makes you go through that whole procedure. But that's not to say that I can't ask anything or something about the concepts.
Yes. And for sway column, like you previously mentioned, I just want to make sure I have the idea right. So to consider if a column is braced or sway, is it just its relative strength compared to what it's connected to, sort of? Whether it's depending on its own strength or a strength of a different member to stay up?
That's a better way to say it.
Is that
Yeah. That's the better way to say it. And it is confusing. I apologize. It's a confusing topic.
Yeah.
But when they wrote the code, they had to write the code in a way trying to anticipate all kinds of different structures where it's not well defined. But in normal everyday buildings, it's a lot simpler than how we have to present this. In normal everyday buildings, if your concrete column is relying on something else for the lateral support, and remember, lateral is basically wind and seismic. So if your concrete column is relying on something else to hold the building up laterally, then it's braced. If the concrete column is part of the system that is holding the building up laterally, then it is not braced.
Okay. Thank you.
Sure, sure.
And are we just supposed to know it conceptually? There's no calculations or anything on the sway, brace and non-braced columns?
Yes.
Okay.
Yes.
Thank you.
There are some calculations that I presented, but those calculations are only for questionable, very rare questionable situations.
Right.
Like I put it before, a structure that everybody is familiar with, the Cal Poly Pomona parking garage, I think it was 4 or 5 elevated concrete deck parking garage. In that parking garage, some columns are much, much larger than most of the columns, and they're all connected by big, thick beams. Those are the moment frames. The columns in the moment frames, those columns are sway columns because they are what's holding the building up if there's an earthquake. All the other columns in that building are much smaller. They're like 24 by 24 inch columns, and they are not holding the building up under lateral forces. They're just going along for the ride and carrying their fair share of gravity, but their resistance to the earthquake is insignificant compared to the moment frames. So
Yeah.
they would be braced. So a very common example, the Cal Poly parking garage, some of the columns are sway, most of the columns are braced.
Okay. Thank you.
Sure. Anybody else? Any other questions?
Professor, could we please go to your homework 7 when you posted the answers for it? You put ties for the column, and you said that the spacing was 7.11. I'm 7.1 something. I'm not 100% sure what the exact number was, but whatever I did and whenever I asked the classmates, we couldn't get that number. I was
Okay.
just wondering how you got the spacing for it.
Okay. That was homework 7 solution.
Yes.
Okay.
But yeah, 7.11.
Okay. And are we on the right page?
Yes, right there on the right side.
Okay.
It says it's bigger than 6.
Oh. Okay. Yeah, that's a good question. Okay. This was from the very first lecture that we did on columns. Before we even got into the design of columns, we talked about tied columns and spiral columns. And when we did the tie columns, we had, and I know it was an avalanche of information. So I don't blame anybody. They have to go back and kind of regurgitate this stuff. There's a lot there. But one of the one of the giant snowballs in that avalanche was that when you're detailing columns here, if I had 8 bars like I'm showing, if the space between the bars is less than 6 inches, then you don't have to put these cross ties in here if you don't need them for any other reason. You don't have to put them there. But if the space between these 2 longitudinal bars is greater than 6 inches, and 6 inches is just an arbitrary number given by the code. That's what the code says. So if it's greater than 6 inches, the code says you have to put intermediate ties in here to keep these bars from buckling. So the 7.11 came from 20 minus an inch and a half, minus an inch and a half, and then using the procedure that we did when calculating the minimum width of beams, where this bar is in the corner of a tie and the corner in the tie. And then so basically I just calculated what that space was between them. And I came up with actually I probably didn't even come up with 7.11. I probably drew it all to scale and had 7.11. But it was just illustrating that this space is bigger than 6 inches. So therefore this tie and this tie are required.
So it's not from center to center has to be 6 inches. It's in between has to be 6 inches.
I knew you were going to ask that.
Oh.
I forget because they recently changed it all. They recently changed. It used to be there's all these different requirements, and it used to be like center a bar to center a bar, but it got confusing because that space is bigger and this space is smaller if the bar is on this side and not that side. So they recently changed it. So let me see what they changed it to, because they may not have changed that part. Okay, design, introduction to columns, types of columns, load capacity. I think that's in the neighborhood there, 259. Okay. Well, his picture is not any better than my picture. I'm looking on page 267. And let's see where he says it. Yeah, figure 9.4 on page 267. But that looks like this. Oh, it is. It's the space between the bars, not center to center of the bars. Yeah.
Okay, now it makes sense.
Yeah.
So pretty much it's going to be 20 minus 1.5 minus 1.5, and then the diameter of number 3 ties, I believe we used, and then twice of that, and then minus 3 of the diameter of the rebars, and divide by 2, whatever we get.
Close, but I think there's a bit of a space in there because that main steel is not hard up against the side of the tie. It's wedged right in the corner of the tie. So you're very close, but there's a little bit of a discrepancy there. Let me try to elaborate a little bit what I just said. So here's the column. There's the tie, sort of. And this rebar in columns, that rebar is shoved right there in the corner. So it might be hard up against the tie like that, or the radius of the tie, there might be a little bit of a space. It depends on how big that bar is. But really, we're just, for all intents and purposes, what you said is fine. Okay, that was 2. Anybody else have any other questions before Edgemond has 3? Okay, Edgemond, you want to do your third one?
No one's asking?
No one's asking.
All right.
I think everybody's very confident.
Professor?
So
I
yes.
have a question on the development length. So for when we were doing footing, we found the development length parallel to the ground. but today we were doing perpendicular to the ground. When, under what case would we do each of them?
Okay, that's a great question. Let me, okay. Now, are you guys able to see just a big blank white?
Yes, yes.
Okay, great. All right. And let me draw. Oh, I didn't want to draw that. That's really bad. Hey, stop that. That's weird. Okay, hold on. Something's going. Whiteboard, share, eraser. There it goes. Okay, I don't know what that was. There we go. All right, so here's the footing, right? And you could have a wall or a column here. And you have rebar down here like this, okay? And what it's all about is you have to look at where your failure surface is, your critical surface. So if I'm designing this rebar, where am I asking this rebar to take the most load? Where is the critical section for this rebar?
Right at the column?
Right at the face of the column, right
Yeah.
there,
Yes.
right? Okay, so that means, do I have enough length from the end of the bar to the face where I need it, that length right there, do I or do I not have enough to fully develop that bar? Okay, so now to your question, I also have rebar in my column. Now I'm just going to show it like this, even though that may be unrealistic. I'm just going to show it like that. So where's the critical section for this rebar? It's right at the bottom of the column, right? There's my critical section. So do I have enough length to develop this rebar? Well, my length to develop it is this distance right there, which may or may not be enough distance to develop that rebar. So to your question, every time and any time you have rebar that terminates, you may have a situation where you have to check that development length. So if this was my design, I would have to check it here, and I have to check it here. And I'd have to check it anywhere else that there may be some suspicion that I haven't satisfied. So basically what the code says is, you got to make sure that is adequate all the time. It always has to be checked and made adequate. And so it's kind of up to you and me. We're the designers. We're not going to run LD checks, for every single piece of rebar we ever use, but we have to use our engineering judgment to spot when it might be a problem, when there's an issue.
Okay, so we essentially only do the vertical one when we're designing the column rebar. And the horizontal one is when we're looking at the footing section. Is that a correct way to say it?
No, no. When you're the engineer, you're designing the whole system.
Sure.
In fact, you're responsible for the whole building. So you may design the column in one afternoon. You may sit down and say, okay, I'm designing columns. And then on a different day, you're designing footings, and you're subdividing your work in a way that makes sense to you as you're designing your work. But the construction doesn't care if this rebar is part of the column or this rebar is part of the footing or what. It doesn't care. So at some point during your design process, you are going through all these connection details, and you have an eye, you have an eagle eye that's looking out for something that might be a problem. That's really what engineering's all about, right? We are the experts looking to figure out where the problems are. Some people call us pessimists. The glass is always half empty, or quarter full or whatever, but that's our job. Our job is to find the problems before nature does.
Right.
If nature finds the problem, it costs 100 times more than if you find the problem. So what you said is not wrong. I'm just kind of, the thought process is you're looking at this whole detail, and it's not the column design, it's not the footing design, call it a connection design. But at some point, you're going through this and going, wait a minute, that ain't going to work. That's going to yank right out of the footing.
Right.
Okay. Now, to add to your question, just briefly here, when you have a beam, like we started this class with, and you design your, wow, I can't get in there any closer than that. There we go. I'll do it like that. Okay, so you design your reinforcement for the beam. Usually, in a beam situation like this, usually the rebar develops much faster than your moment does in a beam. So the moment is this parabolic shape, and the rebar is developing in a linear fashion. So usually, if you drew the capacity diagram over the moment diagram, like we went through, you'll see that the capacity of these rebars is developing faster than the moment does. So usually you don't have to worry about this situation in terms of development, but that is not always true. And I gave you that anecdotal story of my senior project, where in my senior project, I built a beam that had proportions roughly like this. And then I had my reinforcement in here like this. And I put point loads right down the middle here like this. And so this load created a moment that developed faster than the rebar did. And when this thing failed, it actually was a bond failure. It did not develop the full flexural strength that it was supposed to develop because it suffered a bond failure before it got there. So this situation here, and again, this is the mistake I made. This is my senior project and I messed this up. So it's not always that obvious, but the mistake was the moment here is developing much faster than the rebar is developing. I should have recognized that by looking at my own details, and I should have put some hooks on here to guarantee that the rebar would not have a bond failure before it yielded. Okay, does that help your question?
Yes, sort of.
So,
So
They
why do small bars develop faster than big bars?
because they're smaller. It's a surface area to bar size deal.
Oh, so it's a
A
function of surface area?
Oh, sure, because rebar is being developed by the ribs, the lugs in the steel,
Right.
and the friction and the chemical cohesion, adhesion. So
Right.
it's the surface area and the lugs all the way around the surface area that are developing the bar against the area of the bar itself is what you're trying to develop. So like the 0.6 or 0.44 or 1.27, whatever the area of the bar is, times yield is the force that you're trying to develop. So the smaller the bar is, the more surface area you get in proportion to the area of bar that you're trying to yield.
Makes sense. Thank you.
Okay. Yeah, no problem.
Professor,
Yeah.
is that why in your notes you wrote that the LD minimum is 12 inches?
Well, that's what the code says. LD minimum is 12 inches because you could have like a number 3 bar that calcs out at like 9 inches, and they wanted to put some kind of a minimum there.
Oh, okay, makes sense then.
So, but it's the relative proportion of the perimeter to the area. And it's, hopefully this doesn't confuse you guys, but it's kind of like the same principle as why are there not, why are all ants like between 1/8 inch to 1/4 inch maximum? Why are ants really small? Why don't we see ants the size of a dog? Well, it's because of the surface area to volume proportionality that ants just couldn't make it if they're too big. Things don't scale up the same. So it's the same with, I don't know if that helped or not, but it's the same reason you don't see bacteria the size of a Volkswagen and you don't see ants the size of a dog. The proportionality doesn't scale up like that. So it's the same thing with rebar. Okay, still have half an hour. Who's got some questions?
One more, Professor, for
Sure.
cracking and deflection.
Cracking and deflection, yes.
So the concept behind how live load can't be found on its own, but instead minus of the whole dead plus live minus dead, is it because the nature of uncertainty of the live load?
No, it's not. No, it's not. Good question. It is, the uncertainty of the live load is a whole different ball of wax.
Oh,
It is, I'll draw you a little picture.
Okay.
Hopefully this will help. This is just not working. Let me kill that. Go there, share my screen and share. Okay, can you guys see the lecture?
yes.
Okay, I'm just going back to this to get me like a clean sheet of paper. Okay, and annotate. Okay, so I'm going to draw like a graph, and here's a linear line, okay?
Yeah.
And what I'm drawing, the vertical is the load. Let's call it MU, whatever, just some measure of loading. And down here is delta, deflection, okay? So I put on a little bit of moment and I get some deflection. I put some more moment, proportionately, I get more deflection. But this line takes a detour when the beam cracks. The whole problem is that the darn concrete is always cracking on us. So when it cracks, it does this. The slope of this line is the gross moment of inertia times the modulus elasticity. The slope of this line is the cracked moment of inertia times the modulus of elasticity. I'll put these in here. So the slope is EI gross, and the slope of this line is EI cracked. Okay, so when the beam cracks, it suddenly is not nearly as stiff as it was before it cracked. So for the same given loading, it's going to deflect a lot more after it has cracked. So does that concept make sense?
Yes.
Okay, great. So now what we're doing when we're finding these deflections is instead of calculating the exact path, we're using that Branson equation, which is a shortcut. So what that Branson equation is doing is drawing a line from here. Actually, pardon me, sorry. Let me change the color. It didn't change color. Change color. What is the, all right, I give up. Yeah, there it is, okay. So the Branson equation is calculating a point somewhere out in here. And the slope of the blue line is EI effective. And that Branson equation, the one with the MA over M cracked to the third, that's the effective moment of inertia equation. And it gets you a true deflection for a given load, just like that. Okay, so instead of going up and over, you're just doing a straight shot to get to that deflection that you want at MA. But you cannot calculate the deflection due to live load directly, because if, let me try to make sense of this. Okay, so this didn't change. Okay, that time it did. All right, so now, and I use my text. This is M dead load at this point, okay? So to find your deflection due to dead load, you use this effective moment of inertia to get the M dead load. But what happens if you have live load and dead load? Okay, so here, text. Okay, so this point is M dead load plus M live load, right? So this level of load is M dead load plus M live load, and then the effective moment of inertia that you calculate with that gets you, what is the deal? Gets you from here to here. Okay, so now I'm going to answer your question. All that was to get to how I can answer your question.
Yeah.
You have to calculate the M dead load plus the M live load delta here, because of the dead load is what caused it to crack in the first place. And so you are calculating what's happening post cracking. So a big portion of the total deflection is after cracking. Only a little bit of the total deflection was before cracking. If you try to calculate the deflection due to live load by itself, then you would have this situation where M live load would be right here. So if I just started from 0 at M live load, that would be here. So you would calculate this deflection. You'd calculate only this much deflection right there. But look at what you're doing. You're calculating the deflection based on the gross moment of inertia with M live load. But that's not real at all, because M live load never occurs by itself. It always is on the trailing end after the dead load. So the answer to your question, you cannot do it because the dead load caused the beam to crack. And once the beam was cracked, the live load is following this cracked path here. You can't go back to an uncracked section to just do the live load by itself. It's always on this post-cracked trajectory after the dead load. Please tell me that made some sense.
Yeah, it did.
Okay.
So now that raised me another question. So if there a case where the dead load alone hasn't caused it to crack, but the live load is the one that makes it go past the cracking point?
Sure, absolutely.
So
Yeah.
in that case, would our I effective before dead load only be just IG?
Yes, it would. So if this is just your dead load down here and you haven't even cracked yet, then when you calculate IE, what you're going to get is an IE that is greater than I gross. So you have to look at that and say, whoa, wait a minute. I effective cannot be greater than I gross. I'm just going to use I gross. But then when you go to check your dead load and live load together, now you're going to be way up in here someplace, and your IE will be a true number.
I see. Okay. Thank you.
Sure.
Professor, can you jump reference lecture 15, please.
Sure. Let me,
Example 5.
okay.
It's gonna be example 5. The right when we're solving for the development length.
Oh, okay. There's example 4.
Almost there.
Okay, example 5. And
Right.
then,
So development length.
okay, we went down a little ways. Checking, punching, shear. Okay.
Once all that got good to go,
Recheck one-way shear. Okay, right there.
there it is.
There it is.
So that development length formula, I know it has so many variables in there. One specific one I wasn't too sure was the C sub B value.
C
where
sub
you
B.
have to,
Yes.
where you have to pick the smaller of either the half spacing of a rebar or center of bar to nearest face. That center of bar to nearest face, I can't visualize it, or I can't see what bar, because I try to visualize it, and I was taking the dimension from the center of a bar to the outer face, and I just wasn't getting 3.5, or I'm not too sure how to go about that.
Okay. No problem. So if see this image on the screen right now?
Yep.
In fact, let's do this from the current slide. Okay, see that's a little clearer. Now, if I take this image, if I was to take it and I slice this footing right there through the red, which is a critical section anyway. So I slice it right through the critical section and I look at that plane.
Mm-hmm.
What am I going to see?
Well, the fluxual steel, it's in and out of the page in
That's
this
right.
view.
Yep, that's exactly right. So this is the section here, right?
Right.
And then you're going to see, I'm not going to draw all of them, but you're going to see the flexural steel coming in and out of the page, just like you said. Okay, and then there's like 15 more of them in between them. But that dotted line rebar is this rebar coming in and out of the page.
Okay.
Okay, so now the C sub B is the distance, that this is the definition. It's the distance from the center of that bar to the nearest concrete face. The nearest concrete face is directly below it. That's the bottom of the concrete.
So it's 3 for the clearance space, and then half for the rebar, or?
Yes, that's exactly right. 3-inch clear cover is required by code against earth, and then plus, and this is just rounding, but plus a 1/2 inch for
Okay, that's
bar diameter.
Yeah. Okay, so that half was rounding, because I know there was like some of the bars here that I used. Or this bar, I don't think it was exactly half, but it's okay to just say it's half.
Yeah. Well, that's an absolutely valid question. These things are just not made that precisely. What they're going to do is take the rebar and they're going to build a mat out of that rebar, and you're not even sure, as I've said before, which ones are going which ways, but you're going to have a mat of rebar where half of them are going this way and half of them are going in and out of the page. And then what they do is they set these guys on what's called adobes. They're little concrete blocks. And they just put them on there. And these adobes are 3 inches high. So if this bar is, say, a number 6 bar, then this is really 3 plus 3/8 because half of a number 6 bar. If this is a number 10, then it's really 3 plus 5/8 or something like that.
Yeah.
But for the purposes of designing these footings, half inch to get to the center of the bar is close enough. And then I would think that, if this was me designing this, then when I got down to the actual nitty gritty, then I would refine that and I would make CB. Once I know what size bars I'm actually using, like once I got to here, 15 number 10s, then I would use a more refined value in there. But it's not going to change by much. It's, instead of 3.5, you're going to have 3 plus 1.27 over 2. It's going to be 3.64.
Right.
So.
Okay. Yep, that clears it out. That was it.
Okay, good.
Professor, I have a quick question. I don't know if you could refer to homework. Which homework? Homework 7, problem 3.
Sure.
I'm trying to redo the problem, and at the very end, when you calc the moment, I was wondering how you get this distance of 9.
Okay, let's get to, you said problem
3, the last
3.
one.
All right, and then this page or the next page?
The next one.
Okay.
The very last step when you calc the moment.
Oh, yeah, right there.
Yeah, that 9.
That 9. Okay. I don't know.
Wasn't sure where. I looked through the other work and I was having trouble finding where, like how you were able to determine the distance to those forces were 9.
Okay. Oh. Yeah, okay. All right. Okay, I got it. Scared me there for a minute. I got it. Okay. So, good question. What I did was this particular problem, the entire section is in compression. And we talked about this a little bit the other day. So because C is 36, then A calculates to be 28.8. Because 28.8 is greater than 24, the entire section is in compression. And it's the same compression. Even though the strain has this inclined slope to the strain, the compression is still taken to be 0.85 times 5 KSI. So all of that is to say is that the concrete force is right down the middle of the column. So P sub n is assumed to be right in the middle of the column, but because of the geometry of this one, A over 2 is also right in the middle of the column. So P sub n is pushing down, C sub c is pushing straight back up, all at the center of the column. So to sum my moments, I didn't do it the way I've always done it and the rest of them, which I think is a mistake. I always summed my moments from the far edge. This time I summed my moments about the center because I took advantage of these forces right down the center, kind of canceling each other out. So back to your question, where did 9 come from? Half of 24 is 12. So that's 12. 12 minus 3, the distance from the rebar to the center is 9.
Okay. And you report the answer in feet. So I'm assuming you did, because that's in inches, right? The 9?
9s are inches, yes. Yeah,
So you probably just converted.
I did.
Okay.
72.5 times 9 minus 120 times 9. is 427.5 kip inch divided by 12 is 35.6 kip feet. Yep,
Okay.
yep, you're right on the money.
Thanks. I was thinking it was 9 feet and I was getting confused, but
I
that makes
bet.
sense now.
Yeah.
I appreciate it.
Okay.
Professor, I had a
Yes.
quick question when there's soil on top of the footing.
Sure.
So whenever there's soil on top of the footing, I don't understand what it really changes because we didn't have it in example 5, and we like didn't even use the soil in most of our calculation. Like for shear and everything, we didn't even like touch on the soil. We
Okay.
we only
Okay.
used it to find the B.
That's right. That's the only thing you do use it for. Okay, so here's how it works. When I put in a footing, what they do is they dig a hole, right? So they just use an excavator and they dig this big old hole. And then we fill part of the hole up with concrete. Blup, 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 blup. That fills up with concrete. And this concrete weighs 150 pounds a square foot. And then if you have this situation, they may come back in here and backfill all of this with dirt. So when the geotechnical engineer says that the maximum bearing pressure allowable is such and such number, you have to take away from that bearing pressure number by what you've put over the whole thing, namely so many feet of concrete and so many feet of soil takes away from this allowable bearing pressure that you might otherwise have for a point load coming down from above. So on the size of the footing and the allowable soil pressure, any overburden, as this is called, takes away from your allowable soil pressure. Okay, so that's part 1 of the answer. Okay, part 2 of the answer. Here's my hole. And here's my footing. And thinking about how to do this so it makes sense. Here's the column coming down on this. And then we have some backfill or overburden in here, okay? Now, the column has a fairly substantial load coming down from the column. And the footing weighs something and the soil weighs something. But for concrete design, we factor all these loads and that soil pressure goes way up because now the soil pressure is due to factored load, not service load. But that's okay because I don't really care what the soil pressure is anymore. I've already checked the soil pressure. All I care about now is what that soil pressure is doing to the concrete. So now what we have is this soil pressure is coming into the bottom of my concrete, and it's equal and opposite in magnitude to the force of the column coming down from above. So the load is coming from the column and it's loading up the soil like so. But all of this load from the column has to go from the column and it has to spread out through the concrete to evenly load up the soil. So this load coming down from the concrete column and spreading out is what causes flexure and shear in the concrete footing. So it's only this load that I care about that is spreading out and causing flexure and shear in the concrete. The load of the soil overburden and the weight of the footing itself, I don't care about because those loads are going straight down through the concrete, and it's not putting the concrete into flexure or shear. So I don't really care about it. It just harmlessly goes right through the concrete and into the soil, we've already designed our soil in this step to account for the weight. So the soil's not being overloaded. The concrete's not being overloaded because that load goes right through the concrete. And therefore, I don't consider the weight of the footing or the overburden when calculating VU and MU in the concrete footing.
That makes so much more sense. Thank you.
Great, good. Okay, we just have a few minutes left. Any other questions?
Any advice for the final?
Yes.
Just not
I
a
do.
vague one. Not a vague one, though.
No. Same advice I give on all of my tests. Taking tests is as much about what you know as it is about knowing where to find what you need to know, as it is about managing your time. Okay, let me say that again. It's very, very important. Taking tests is as much about what you know as it is about finding what you need to know, as it is about managing your time. So when you take my tests, you have to manage your time. Don't try to memorize everything because you can't, but know where to find it in your textbook. That's why it's there. So you manage your time by practicing these. Don't just study the material and memorize what everything is. You have to actually practice them because it's the act of actually running through these examples and practicing them that will make you fluent and be able to do this in a timely manner on the test. But by the same token, when you're taking the test, if you get stuck on one problem, the worst possible thing you can do is to spend an hour and 45 minutes on one problem, nail it perfectly, and then leave 3 other problems completely blank and you flunk the whole test. Okay? It is so important, it is so vital that you keep an eye on how much time you have. There's going to be 4 problems. Some are going to be easier, some are going to be harder, but watch your time. Make sure that you give enough time to fully address each one of the problems. I recommend that you go, before you even start attacking this test, go through all 4 problems first and get a gist of how complicated they may be, and attack the hardest one first. Not necessarily problem number 1, maybe problem number 2 is a lot harder than number 1. Do that one first, but keep your eye on the time. If you put a 75% effort on one problem or on all of the problems, you'll do far better than a 99% effort on one problem and 5% on the other 3 problems. That will get you nowhere. So manage your time. And this is a very, very important career skill. You will carry this the rest of your life. Managing your time and making the best do of the resources that you have. Okay, so now that I've said this, what you know where to find what you need to know, and manage your time, the next most important thing is read each one of the problems or each part of each problem very carefully. Read the problem carefully. Do not assume because the diagram looks exactly like a homework problem that you just spent 6 hours on. Do not assume I'm asking the same thing. Don't freak out and say, well, it took me 6 hours to do this and the homework, I'm never going to, and you just implode. Don't do that. Read the problem. I know that some of these problems take a lot of time, so I'm not asking you to do every single part of every single problem. Read specifically what I'm asking for you to do and answer only that. Don't answer every possible way you could answer it. Just answer what I'm asking for. And then by the same token, when you get to 10 or 15 minutes left of the test and you're just kind of dotting the I's and all that, go back and make sure that you have actually answered what I was asking for.
Just to add on that answering exactly what you're asking for example, like the recent homework we just had, homework 8, I know you didn't, on the statement, you didn't mention anything about drawing a sketch. So in an exam, unless otherwise noted, we just do exactly what you want to see.
Yes, yes, and particularly more on the exam. Sometimes I, I've done this many times, but that doesn't mean that the homeworks, I still forgot to ask for this or do that or whatever. But on the exams, I'm very particular. So yes, on the exams. I will give you this exception though. I'll give you one exception. If at any point on the exam, you would need to verify your design by checking phi VN is greater than VU, or phi MN is greater than MU, or phi PN is greater than PU, do that. That's always necessary. But but from what you said, if I don't ask you to draw a diagram, don't draw the diagram. And I actually went back through, I'm kind of in the process of writing the test. I went back and put some clarifying marks on one part of it so that it hopefully is clearer to you, the student, of what it is exactly I'm asking for and what I'm not asking for.
Right on.
Okay, we're coming down to the final wire. Anybody have any last minute desperate questions? Let me use the last 2 minutes to tell you this. The test will be administered exactly the same as the midterm. That's what you can expect. So there will be a test that you take through the Respondus, and you have to have a laptop or a webcam or something that can watch you. All of that is exactly the same as the midterm. And then I will create an assignment called Final. And after you have completed and submitted your test, you will upload your cheat sheet and all of your handwritten work to the assignment called Final. And I will grade from what I see on the actual exam, fill in the questions, and what you upload to your work. So let's make sure there's no questions about that. I haven't done this yet, but that's what's going to be there for the final, exactly the same as the midterm. And I think I'm going to set it up so that you cannot take it any sooner than, say, like a half hour before the scheduled start of the test. And you cannot start it any more than, say, a half hour after the scheduled start of the test. I believe the start time of the test, I mean, that's a good question. Let me look at the syllabus. Can you guys still see this? Is the screen still sharing?
Yes.
Okay, okay. So the final exam is scheduled for 5 p.m. to 7:05 p.m. on August the 4th, which I believe is Tuesday. Okay, so thank you, everybody. Everybody who's still on the line here. Thank you, everybody, for your patience with this whole virtual effort. I truly hope that this was worth your while. Thank you again for being with us, and good luck on the final. If there's any more questions, I am not going to have office hour before the final. So if anything else comes up, please just email me and I will do my best to answer it through the email. So thank you, everybody. And yes, have a great rest of your summer as well. Thank you.
Thank you.
Thank you, Professor.
Thanks a lot, Professor.
Thank you, everybody. And I'll post this to YouTube as well.
Thanks, Professor.
Thank you, Professor.
Thank you.
You have a good one.
You too. Thank you.